21%. That is the percentage, according to the US Department of Education, of 9th graders voting mathematics as their most disliked subject. This means that approximately 1 in 5 high schoolers in the Western world dislike mathematics more than any other subject that they take. Or you might even say that they hate it. What's ironic about this statement, however, is that in order to understand it, you need to have a simple enough grasp of what mathematics even is. And it highlights the issue I want to talk about today. I am sure all of you have asked yourselves this question before. Great, so that's cool and all, but when are we ever going to use this mathematics in real life? And I'm sure all of you can find the answer to this question for much more simple topics. Addition, multiplication, finding an area. These are simple applications here. But when we move on to high school, complex numbers, trigonometry, all of calculus, the answer becomes harder and harder to find. It's not as if you're paying e to the power of pi times I euros for your coffee anytime soon. Well, I'm here to show you that not only does it appear every day of your life, but also you might just use it without knowing that you do. Let's start with the obvious. The sciences share the most immediate connection with mathematics, especially physics. But the connection between mathematics and other sciences, although not as apparent, is just as extensive. Think for a second, how much mathematical precision would you need in order to find the chemical formula for titine, the human protein, the longest chemical structure ever recorded, and the longest word in the English language? Or think about some base astronomy knowledge, such as finding the age of the Big Bang using the Friedmann equations. Yes, theoretical evidence might help you a little bit, although I believe that physical evidence is empirical. So I would like to show you this. Please take a moment to feel your ears. Now, what you are all touching is actually a mathematical identity, phi, also known as the golden ratio, defined by the Fibonacci sequence. Well, this is found everywhere in our modern world, from the way the shape of a snail's shell forms to the branches of the trees of your backyard, all the way to the way your blood vessels flow through your body. All of these at least slightly resemble this identity. And there is no coincidence, as this was discovered to be a self-organization principle. What this means is that something or someone without rational thought, such as animals or natural phenomena, would not have the ability to use rational thought as we humans do. Therefore, they need a way to organize their shape in the most effective way possible. And mathematics says it is this identity right here. Funnily enough, this actually comes from Mr. Fibonacci observing the patterns of rabbit breeding. And as funny as that might be, it actually goes to show that this mathematics always existed in our world. We only had to observe it. It isn't some made-up rule that we came up with that just so happens to apply to everything around us. Well, I'm sure the shape of your ears doesn't exactly surprise you, so I'm going to talk about something that's more relevant, something which all of us have to think about at one point or another. Credit cards. Think for a second what a bank company might think when it makes one of its billions of transactions every single day. How much money am I transferring? What's the interest rate right now? What currency am I transferring to? What's the exchange rate? And of course, does this person even have enough money to buy what they're trying to buy? Well, all of this comes from computer science, an area which is very relevant to our modern world. from our credit cards to the phones I'm sure all of you own. It builds the structure of our current technological world. But the reason I chose credit cards as my example is not because it only links to computer science, but also because it's related to another area of human learning, which I wanted to bring up: economics. Computational economics is an area of economics that deals with the use and creation of economical models in order to solve complex issues. Think of it this way. Imagine if we had a somewhat perfect replication of how our world functions, and we were able to test any hypotheticals on this made-up world of ours. Well, that's what computational economics tries to do. And one important mathematical area that plays into this area is mathematical optimization. Between you and me, I don't fully understand it myself, but mathematical optimization is the act of trying to solve a problem where you have 2, 4, 1,000, an infinite number of choices, and you're just trying to find one, the perfect one, that fits multiple choice criteria, ending up looking something like that. Well, think about it this way. How would a government be able to decide how much to tax a product without causing a potential market failure or harming consumers more than they should? This is our answer in our current times. Although this optimization is not only used in economics, it is also used in vehicle routing, network management, and even schedule building. So, if you're ever looking forward to studying that economics degree, as it is one of the most wanted degrees of the current times, I think you should be paying a little bit more attention to your calculus section of your math class. There's another skill that most economists use in their analysis, however, and that is demography. That's right, the study of people. Remember the statistic I brought up at the beginning of my talk about the 21% of high schoolers voting mathematics as their least favorite subject? Well, I went ahead and did a little bit of my own research, not from a Western audience, but from an international one. Not only that, but I took multiple levels of education at play to check if it truly is the more complex mathematics that is the issue here. And as we can see here, fortunately enough for me, mathematics is still the most disliked subject out of all of these. What's interesting about this, however, is that this percentage decreases from early school life at 24.6% to 15.3% in high school life. My theory here is that all of this excess percentage just went to subjects which have similar ideas of thinking, perhaps economics or physics, as aforementioned before, and have made people focus on these areas rather than the general concept of mathematics. And this gives this data meaning. This rational and cold calculation of numbers gains meaning if you just tweak your vision a little bit. One shocking instance of this, however, comes in language learning. If you were to take a look at this otherwise unrelated language problem and this set of mathematical identities, you could say that language learning is nothing more than a very, very long unknown problem. Think of it this way. When you have an unknown problem, you use the information you are given to find the values of certain unknowns, and you use those unknowns in order to find everything else, creating a final solution. In language learning, you look at the context clues you have in front of you and assign meanings to words. You use those meanings to learn harder vocabulary, harder grammar, and eventually reach fluency, the solution to your so-called problem. Now, this is a method which I have used myself, and I believe it to be quite effective. Maybe a math major, such as myself, might be interested in using this method in language learning something which would otherwise not be catered to them, or a linguistics major intrigued in this method might understand a little bit more of what makes this mathematical thinking I talk about. But perhaps the most shocking comparison here is that mathematics permeates through the fine arts, specifically music. If you were to take a look at this, although not seemingly, this is the base of what we know today as modern music theory, all the way down to its basics. And these are called overtones. Britannica Dictionary defines overtones as a resonating frequency above a lower bass frequency. But that definition is way more complicated than need be. In reality, this is nothing more than that soft ringing you hear in your ear after you strum a guitar chord as hard as you possibly can. Ironically enough, this soft ringing is precisely how we found all of the music theory we know today, or rather almost all of it. If you were to think of it from a mathematical perspective, all of these are sound waves. If we were to take their frequency and multiply it by 2, by 3, by 4, and so on, we would get the second overtone, the third overtone, the fourth overtone, and so on. What results here is that we get different pitches that ultimately end up repeating. This is why a piano is just an endless repetition of A to G rather than an endless number of unnamed notes. And this also describes why we know most of what we know in music today. I'm talking intervals, scales, harmonics, using simple harmony, and even down to the emotion you might feel during a song. Say you're listening to an emotional instrumental song for once, and you might think, oh, this makes me feel conflicted, but I don't know why. That's nothing more than dissonance and consonance, the act of these waves clashing against each other or harmonizing together. Even down to the emotion, music is dictated by mathematics, which is extremely interesting to me. Having been passionate about both music and math for most of my life, I find it extremely interesting that a subject catered to a creative needs a component that is reliant on such cold, rational calculation. And yet, you quite literally cannot walk far without bumping into it. All of these examples I gave here are no coincidence. You must all realize that mathematics is perhaps the most complex tool we have at our disposal to solve anything and everything which the world has to offer us. Even from its very inception, mathematics has been made to cross borders, languages, and areas of human learning. It is perhaps the most developed we'll ever get in solving anything. So, we should be careful the next time we answer that aforementioned question that we are never going to use it in real life, because you are quite literally going to see it and use it every day for the rest of your life. Thank you for listening.